Well, hello. Today we're going to start talking about probability. And in this lesson, we're going to be discussing empirical probability and theoretical probability and just a bunch of very basic ideas of probability. Okay, so nothing too fancy in this particular lesson. All right. So a couple definitions that we need to get a hold of that we're going to be discussing. An experiment is a controlled operation that yields a set of results. Outcomes, those are the possible results. And then an event is a subcollection of those outcomes. So let's put something to this that might make it a little more tangible. Maybe an experiment that we're going to do is we're going to flip a coin and record the results. So our experiment might be flipping a coin, recording the results. The outcomes, the possible outcomes, are either heads or tails. And then an event, the sub-collection of outcomes, maybe the event is did we get a tail or not? Okay, so that could be the event. Or maybe we flip a coin 2 times, in which case we actually have 4 possible outcomes. We could have heads, heads, we could have tails, tails, we could get tails, heads, or we could get heads, tails. So these are 4 outcomes. Now, maybe an event might be what's the probability that we got at least 1 tail? Or what's maybe how many times did we get 2 tails? Okay, so those are some outcomes and events, and we'll look at several more examples as we go. I just wanted to start out with that. Now, there's 2 types of probabilities that we're going to be discussing today. One is called empirical probability, and this is also known as experimental probability. So some people call it experimental probability, some people call it empirical probability. They both mean the same thing. And what it means is you're actually going to do something and record the results. Now, there's also theoretical probability. Now, theoretical probability is most of the time what people think of whenever they hear probability. They feel like, oh, you're actually doing math. That's the theoretical probability. Like, what's the probability of rolling a 1 when you roll a die? Well, it's like 1/6. Okay, what's the probability of flipping a heads on a coin? It'd be 1/2, 1 out of 2. There's 2 sides, etc. Now, empirical probability, this is the experimental probability. This means you actually do something and record the results. We can do empirical probability on flipping a coin. Maybe you flip a coin 100 times and see how many times you got heads. Or maybe you roll a die 50 times and see how many times you got 6. But that's really not the best usage of empirical probability. This is typically used whenever you really can't do theoretical probability. Or maybe you want to check to make sure that it's a fair die or a fair coin. So then you could do some experimental probability to see if it matches up. But a great place where you might do empirical probability might be like, maybe I could say, what's the probability that someone that attends this school drives a red car? Well, I can't really know that. I mean, even if I went down to the office and I got a list of everyone who has their car registered, I don't know what days they're here. I don't know how often they drive. It would be really tough. So instead, since I can't really know all that information, plus some people don't register, they just show up, they don't try. So what I could do is I could go out to the parking lot and I could go down one whole row of cars, and maybe I just write down, I walk down one whole row of cars, so there's cars in all these parking spots, and I could just be like, okay, well, let's count how many red cars there are. So out of these 20 cars, there's a car here, one here, one here, one here, one here, one here, one here. And maybe out of these 20 cars, maybe 4 of them were red. And so then I might say 4 out of 20, or that comes out to be 20%. So that's an empirical or experimental probability. A lot of people have a hard time understanding what that is. We typically use empirical probability when we can't do theoretical, or if we want to check it and make sure that everything's on the up and up. Okay, so when we do empirical probability, it's just going to be the number of times that an event occurs divided by the total number of times that we perform the experiment. In the last example we did, we walked down a row of cars. We recorded the fact that there were 20 cars total, and then we also said that 4 were red. And so the probability of that is 4/20ths, and then you can divide that out, and that gets you 0.2, or 20%, as I said. Now, probability is always a number between 0 and 1 inclusive. That means that it is possible to have 0 chance of something happening. Or it is possible that every single time it happens. Okay, and this is especially true in empirical probability. If I were to walk down a row of cars and look at 20 cars, there is a very real chance that I got 0 red cars out of those 20. Now, does it mean that 0% of people who attend this school drive a red car? Maybe, but probably not. This is just the best that we could do. In our example, in our experiment that we did, maybe we got 0 red cars. Sometimes that happens. Okay? All right, and 1, of course, means that it always happened. Maybe we walked down and for some reason, there were 20 red cars. And then we would say there's a 100% chance that somebody drives a red car according to our experiment. Again, probably not true for the whole population, but in our experiment, that's what happened. So let's say we end up tossing a coin 100 times. So we toss the coin 100 times, 44 times it lands heads up. Find the empirical probability of coin landing heads up. Okay, well, what we're going to do is we're going to say it was 44 heads out of 100 total. So that means then that it was 11 out of 25, and then we can take that and turn that into a decimal. Like, this is a perfectly good answer, but we also like writing things as decimals, and we also like writing them as percentages. These are all equivalent ways of saying this probability. So probability is always a number between 0 and 1 inclusive. You can never have a probability of 110%. Some people are like, oh, I'm going to give my effort, I'm going to give 110% effort. Let's not just worry about that. But in probability, it is impossible to have a number larger than 1. If you have a number larger than 1, you did something wrong. Just like you can't have a negative number because you can't have anything less than 0. All right. Here we go. A pharmaceutical company is testing a new drug, and it's going to help with a weight reduction. The drug is given to 500 individuals with the following outcomes. 379 lost weight, 62 had unchanged weight, and 59 actually gained weight. Now, the pharmaceutical company, they can't necessarily know how their drug is going to be received by the public until they do an experiment. So they do an experiment. In this case, they have 500 people that said they'd take this drug. So they do this experiment, and now that they've done this experiment, they can actually answer some probabilities. Find the probability that somebody's weight reduces when they take this drug. Okay, well, what we would do is we would say the probability of reduced weight, and we just do that, we just say capital P, right? This typically means probability, and then we put inside parentheses what we're looking for. In this case, the probability of weight reduction. Then this is the number of people who lost weight divided by the total number of people. So in the experiment, not all the people in the world, unless that's what you're doing. But 379 out of 500 lost weight. So this particular weight loss drug seems to be fairly effective. 75, almost 76% of people lost weight. Now, there were also some people who did not gain or lose weight. They just stayed the same. and it came out to be about 12%, 62 out of 500. And those people would take the drug and they'd be like, well, it really didn't help. They don't know. But then there's this other group of people where they said, I took the drug and I actually gained weight. And it ended up being about 12% of people gained weight. Now, if you go through and add all these up, these should add up to be 100%. Okay, sometimes they won't. Sometimes it'll add up to be like 100.1, or it'll add up to be 99.8, and that just deals with rounding error. So don't be too concerned about that. But sometimes that does happen. Okay. There's something called the law of large numbers. Now, the law of large numbers is actually abused by a lot of people. Um, it just says this that the law of large numbers applies to things that happen in the long run. After many, many, many trials, here's what would happen in a large portion of them. That's what the law of large numbers means. It does not mean what's going to happen next. And this is where this idea is abused by many people. There's a lot of people like maybe they'll go to Las Vegas and they'll play a card game or they'll play roulette and they see that it's come up black like 5 times in a row. And so then they say, "Oh, well, it's come up black 5 times in a row. The next 5 have to be red. So I'm going to start betting on red because red is due. We've got to get some reds in to balance this out." But that's not what the law of large numbers says. The law of large numbers says that like over the course of a million spins, about half of them would be red and about half of them would be black. Now, of course, if you know roulette, you're like sitting in your chairs being like, "What about green? What about when the house wins?" Let's just come off of that for now. All right, don't worry about it. But it means over many, 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 many times, there is never, ever a time that you can use the law of large numbers to predict what will happen next. That's not what the law of large numbers is used for. Okay, so if you ever hear anyone say that, like, "Oh, well, we've had so many heads in a row, tails is gotta be due," well, those people are just very ignorant. Okay, they say, "Oh, the law of large numbers says that it's got to balance out, so we gotta bet tails." No, those people don't understand math. Okay, so the law of large numbers is a long run average. About this many would happen in the long run. Okay, so let's look at something maybe with some smaller values here. You could imagine if you flipped a coin 10 times, I'm going to do one more actually here. You could imagine if we flipped a coin 10 times and you would expect to get 5 tails. But would you be all that shocked if you only got 3 tails? Probably not. You flip a coin 10 times, you would like to think it's going to be 5 heads and 5 tails. But at the same time, if somebody, did like tails, tails, heads, tails, 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 heads, heads, tails, tails, tails. Like, I don't know if that was 10. But you wouldn't be totally shocked. You wouldn't yell out, "Shenanigans! They're cheating!" That's because there's a very small amount. Okay? So whenever you have a very small amount, you can't get too upset if it's not exactly 50-50. Okay, so let's say maybe we do 100 tosses. You would expect 50 to be tails, but maybe you only get 45 tails. Then that means that the experimental probability was 0.45. You could also say the relative frequency. Okay, frequency is a number of times. Relative means like in this experiment, here's what happened. Okay, now you wouldn't be shocked. You wouldn't walk away being like, "Oh my gosh, the coin only came up tails 45%. They're cheating." You probably wouldn't say that. Okay. Now, in 1,000 tosses, you would expect to have 500 tails. Maybe you get 546, right? 54 point or 50, yeah, 54.6% or 0.546. Again, you wouldn't be totally shocked. You'd be like, okay, sometimes tails happens more, right? But what happens here is as the number of tosses starts to increase, this number is going to get closer and closer and closer to 0.500. Okay, if we did 1,000,000 tosses, then this should be really close to 0.500. Does it exactly? No. Maybe 0.510. I don't know. There's some science out there. You guys can Google search it. Which one is slightly more likely to happen? I don't know. Coins are imbalanced and they favor heads. I think that's when you spin them. I think if you're spinning coins, there is a slight preference to heads. So, yeah, something to check out. Okay, but that's the law of large numbers. It means after you do this many, 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 many times, then your experiment should yield a result that is very close to the theoretical result. Right? Now, theoretical result, that's what I, as a math person, I deal with that a lot, and that's what most people tend to think of when they think of probability. The number of outcomes that you want divided by the total possible outcomes. This is where you're not actually doing an experiment, you're just kind of thinking about it. Okay? That's really what it comes down to. So let's think now, probability still is going to be between 0 and 1. You'll never have probability outside of that. Okay? And then these are just, some other pictures. 50-50 chance, you'll hear that, right? 1 out of 2, 4 out of 5, whatever. It's just a picture showing some least likely things that would be impossible and absolute certain things. Okay, that's a 1. Okay, so let's go through and look at a few things. Let's first just be very clear. I assume everyone knows what a die is, but maybe not. We are talking about the little cube that you can roll. It's a 6-sided cube, and they typically have these little dots on them. These dots, if you didn't know, they're called pips. Okay, and so you have like 1, and then maybe 2, and maybe this side has 4. I'm not sure. There's a specific pattern to them. Anyways, on our die, we have 6 sides, and each side is going to have a number or a number of pips. I'll always refer to just the number, though, because you all get it. I hope that if you see this on a die, that we're talking about rolling a 2. Okay. All right. So what's the probability of rolling a 3? Well, how many 3s are there? Number of 3s? Well, there's only one of them. How many total? Number of total sides. How many total sides are there? There are 6 sides on a die. So the probability of rolling a 3 comes out to be just 1/6. What about rolling a 7? Remember, we're rolling a die, not 2 dice. Okay. If we roll a die, how many sides are there that have a 7 on them? Well, dies only go from 1 up to 6. 1, 2, 3, 4, 5, 6. So how many 7s are there? None. There's not any 7s. Okay, so probability 0. What about an even number? Think about how many evens there are on a die. 2, 4, 6. That's it. So that means that there are 3 even numbers out of 6 total. Notice every one of these has a 6 on the bottom. Right? What about a number greater than 2? Now be careful. This doesn't say 2 or greater. It says greater than 2. And if I were to make a list of numbers that you could... let's try that again. If I were to make a list of all the possibilities of numbers that you could get on a die, 1, 2, 3, 4, 5, 6. If I want a number greater than 2, is 2 greater than 2? No. That means we're only talking about these numbers. These are the numbers that are greater than 2. And you can see that we've got 1, 2, 3, 4 of them. So the numerator, or the top of this, will be 4, and the bottom will be 6. Now, it's nice to reduce these down, but you don't have to. You could leave it as 4, 6. You should want to check your homework and whatever you're doing to make sure you use appropriate numbers. But what about a number less than 7? If you look at all the possibilities, actually every single one of these is less than 7. That means that it's 6 out of 6, or just 1. Right? That's 100% chance. Maybe you would rather think of these as percentages. 100% chance. Right? Because that's like 1.0, and you got to move a decimal 2 places. Okay. 2/3, by the way, would be 66.6 repeating percent, or about 67%. Some people think of it that way. Okay. There's something called the probability of not. Now, in a probability experiment, something either happens or it doesn't. And these two events are complementary. Now, depending on what class you're in, but in our class, we've talked about this all the way back in the very first unit when we talked about the complement of something. And we said, if you have the probability of A, then the complement is 1 minus the probability of A. So we did that all the way back when we talked about Venn diagrams and set notation. But all this means is the likelihood of something happening plus the likelihood of something not happening, of that same event not happening, have to add up to be 1. Okay? So an event plus its complement is 1. Now, in this course, and in a lot of things, it's nice to know what's in a deck of cards. Maybe you don't play cards. I know a lot of people don't play cards like they used to. My generation, I'm a little bit older. I grew up playing cards, so I know what's in a deck of cards very, very well. But this is a nice social thing to just know what's in a deck of cards. And a lot of people do play solitaire on their phone still, but we're getting away from it. So let's talk about what's in deck cards. Super simple. There are 4 suits. Okay, they're hearts, clubs, diamonds, and spades. Each suit has 13 cards. They go 1 through 10, Jack, Queen, and King. Now the 1 is usually called an ace. Okay, then we have Jacks, Queens, and Kings. Those are called picture cards or face cards. And then hearts and diamonds are red, clubs and spades are black. Now let's go through and get a look at a deck of cards here. Okay, so grab this image off the internet. I didn't make this one, but this was one that said we don't need any credit to it. It was free to use and no credit, so that's what I'm using. You can see here that we have half the deck is red and half the deck is black. And so you can see that we start counting. We have right here, these are the aces. They have just one little symbol on them. Then the twos, they have 2 of them. Technically, they have 4, but let's not talk about that. So they have 2 of them here. Threes, fours, fives, six, sevens, eights, nines, tens. Once you get to tens, now we go to the jacks. It's a little hard to see, sorry. Then we have queens, and then we have kings. Okay, so we go jacks, queens, and kings. So as long as you can count from 1 to 10, and then remember jack, queen, kings, you're good. You can do everything in a deck of cards. If I ask for face cards, not aces, these are called face cards because down here they have pictures of people, and those people have faces on them. So these are face cards, right? These down here, those are the face cards. Those are faces, not aces. Let's just be clear about that. Okay, so hopefully you can work with the deck of cards. If not, I know they're on the notes packet that I give you, but they are pretty easy to remember. Hearts and diamonds are red, clubs and spades are black, count up to 10, and then jacks, queens, kings. So let's go ahead and look at a couple quick little probabilities about cards. What's the likelihood of getting a 5? Well, let's go back to this one. The probability of getting a 5, let's clean this up here. Get rid of that. All right, so the probability of getting a 5. Let's see, here's my 5. So that's all these. Here's the ones that would be winners, and all I got to do is I could count these up, and I could say, well, look, we've got 1, 2, 3, 4. There's 4 of them. There are 4 5s, and there are 52 total cards. So 4 50-seconds would be the likelihood of getting, or the probability of getting 5. Okay. Let's go back to this, and you can see we have 4 out of 52, and that does reduce down to 1/13. Okay. What about the probability of not a 5? See, here's a great instance where the complement is very helpful. See, not a 5 is the same thing as 1 minus yes 5. So think about how many 5s there were. There were 4 of them. Go back and look at this. How many not 5s are there? Well, I know there's a lot of people yelling at their screen right now, and they're saying, there's 52 cards total. 5 of them are 5s. That means that there's 48 non-5s. Now, you probably didn't go through and count all of the non-fives up. What you did was you took the whole amount and you subtracted off the fives. There are four of them. Right, so all you did was you actually did the complement. You said the probability of a 5 is 1/13th, or you could use 4/52. So I'll take the whole amount and subtract that probability. That gives me 12/13ths, or 48/52. That's also an appropriate answer. The probability of a diamond. Well, there are 13 diamonds out of 52 cards. You know, there's actually an easier way to think about this, though, too. Okay, look, we have hearts, diamonds, clubs, spades. There are a total of 4 suits, all with the same number of cards, and diamonds are one of those 4 suits. And so that's how you can also get 1/4. Now, there's nothing wrong with counting up all 13 diamonds and dividing by 52. That's just fine. Jacks, queen, or king. Like, not pulling out 3 cards, not pulling out 1 card and seeing a jack, queen, king, but rather pulling out 1 card and getting a jack or a queen or a king. Like maybe you're playing some cards, and if you get any face card, you win. What's the likelihood of you getting a jack, a queen, or a king? If we go back and look at this, you can see we've got 12 total face cards out of the 52. Okay, so 12 total cards out of 52 means 3/13ths, or 12/52. This one's always tricky for people. What's the probability of getting a heart club? See, that's what this word right here, and, means. It means pulling out 1 card and getting something that has both hearts and clubs on it. Let's go back and look at this. Look real closely. Count all the cards that have hearts and clubs on them. Remember, it's got to have both. Well, let's see. Here's a heart, no club. Here's some hearts, no clubs, no club. No. Well, here's lots of clubs, but there's no hearts on any of them. So I don't see any cards that are hearts and clubs. The likelihood of drawing a single card and getting a heart club is actually just 0. Okay, so not a heart or a club. This says drawing 1 card and getting a heart and a club, and of course that is impossible. Lastly, a card greater than 6 and less than 9. Drawing 1 single card and having it be bigger than 6, but also having it be less than 9. So let's see, here's 6. That means 7s would work, right? So 7s will work. 8s will work. 9. No, because it said bigger than 7 and less than 9. Not less than or equal to. So that meant there were 8 cards total. 8 of those cards, right? Let's go back and look at them. All the ones that are shaded blue are greater than 6 and also less than 9. So 8 out of the 52. Okay? All right, let's look at one more example. Here's some information about some taco sauces, right? So the table on the right contains some information about a shopping cart full of taco sauce, and they need to be stocked back up on the shelf. Assume that all the jars are the same size and shape, and the stock clerk is just going to pick one at random and put it up on the shelf. He's not really looking. Let's find some probabilities here. Okay, so let's first find the probability of getting a hot sauce. The clerk just reaches in and says, pulls out a jar, is like, oh look, I got a hot sauce. What's the likelihood of that happening? Well, there's a lot of information here. This is what we call a two-way table. We have different brands, and then we have medium, mild, and hot for each of those brands. Okay, 56 total jars of salsa in the cart. That's a serious party. But this one says find the probability of getting hot. So that means we need the total hot, and we're going to divide that by the total possible. So how many hot salsas are there? Don't you dare say 4. Don't say, look, 1, 2, 3, 4. Nope. Those are the different brands of salsa. There are 16 total hot jars of salsa in our cart, and in our cart there were a total of 56 jars of salsa. Right? And so we have 16 out of 56, and here we reduced it down to 2/7. Next, let's find the probability of getting brand A. What's the likelihood that he reached in and he pulls out a jar that says brand A on it? Okay. Um, so brand A, which was a girl that I liked back in elementary school, brand A. So brand A was there were 13 brand A salsas. Then there were 13 out of, man, I'm sorry, I'm still thinking about brandy now. Actually, it was more brandy. So sorry, I guess I should. Um, so we have 13 out of 56. Boom, done. That's it. Now, what about the probability of pulling out a mild salsa? We look at this and we see, I'll let you think about it for a minute. Okay. All right, I'm going to go on. Maybe you can pause it if you still need a second. How many mild salsas are there? There are 21. And how many total? 56. Notice every one of those has a bottom number of 56. That's because that's the total number of jars in the cart. None of that changes. The only time that would change is if we started doing something called conditional probability, which is for another time. Maybe I might say like, hey, what's the probability I pulled out brand A if I definitely pulled out some mild salsa? Or what's the probability I pulled out a medium salsa if I got brand D? Man, there's brandy again. All right, let's get going here. I hope this gives you a brief idea as to some probabilities, and I hope this was helpful. So good luck.